What is the first thing that comes to your mind when you hear the word radio? It could be probably this or this. As you know, this video is all about acknowledging you about the working of a radio, so let's get to the point. Before talking about the radio's receiver circuit, let us brief you about how the information travels to the receiver. FM or frequency modulation is a technique of encoding a signal or information that is the modulating wave or a carrier wave by varying the instantaneous frequency. The frequency deviation in the modulated wave's frequency with respect to the original carrier wave's frequency is directly proportional to the signal to be transmitted. Frequency modulated waves have a greater signal to noise ratio than amplitude modulated waves, therefore are used for voice and audio transmission, that is, in radios. Assuming we all are well equipped with the basics of an electromagnetic waves, we introduce you to a very basic block diagram of a simple radio circuit. First, we have an antenna. Electromagnetic waves after transmission at the receiving end vibrate the free electrons present in the conductor, that is the receiving antenna. These vibrations produce electric field which regenerates the transmitted signal and pass it to the RF amplifier. Then comes the RF filter and amplifier. The role of RF filter can be divided into two parts. The signals present in the transmission medium form a very broad spectrum. So firstly, the RF filter rejects the other signals and gives a relatively small spectrum with approximate bandwidth equal to twice the intermediate frequency around the desired or resonant frequency, or in layman terms, it tunes the signal a little. The selectivity here is not very high. The role played by the RF amplifier is to amplify the received weak signals for further processing, and it is designed in such a way so as to minimize the noise amplification. Mixer and local oscillator. Mixer has two input ports. The amplified and slightly tuned signal from the RF amplifier enters one port of the mixer and a wave from local oscillator to another port. The mixer produces signals comprising the sum and the difference of the input frequencies, and this process is known as heterodyning. Heterodyning produces a constant frequency signal known as the intermediate frequency, which makes it easier for further processing. IF amplifier and filter. This stage contains most of the amplification in the receiver as well as the filtering that enables signals on one frequency to be separated from those on the next. Filters may consist simply of LC-tuned transformers, or they may be of much higher performance ceramic or even crystal filters. Next comes the demodulator or detector stage. Demodulation is extracting the original information bearing signal from a modulated carrier wave. After getting filtered from the IF stage, the received signal needs to be demodulated to harness the information from it. Different demodulators are required for different types of transmission. The basic FM detector senses the frequency variations to extract the information, that is, audio in case of a radio. It should also be insensitive to amplitude variations to prevent the addition of noise. The last is the audio amplifier. The recovered audio signal is amplified as per the requisites of output, and then it is fed into the speakers which convert it into sound. Now we have a rough idea of how a radio receives an electromagnetic wave and make it undergo through various processes to convert it into a song you like. But as this video is a byproduct of our struggle through electrical engineering course, we will have to include circuits comprising resistance, capacitors, inductors, and transistors to baffle you. So get ready. First we have the antenna through which we get the main signal. Below that we have the local oscillator. Now this oscillator is made up of a fixed inductance, inductor L1, and two variable capacitors in parallel. One capacitor has a large capacitance value Vc1 and the other has a small capacitance value Vc2. The capacitor with less capacitance Vc2 is used for rough tuning the radio, and the one with the large capacitance Vc1 is used for fine tuning. This local oscillator is the main component of an FM radio, which helps us to tune to different channels. This is done by the method of mixing the received signal and the signal from the local oscillator. We have the signals from the antenna and the local oscillator passing through this BJT TR1 that acts as a mixer in our circuit. The mixed signal from this goes to BJT TR2, which acts as an intermediate frequency amplifier. This amplifier amplifies only the main desired frequency in the signal and neglects the other frequencies which are considered as noise. For this amplifier, the signal passes through the capacitor C4 and resistor R5, which act as a filter, letting only the desired frequency to pass through, and hence omitting the noise to a great extent. The frequency of LC oscillating circuit is the resonant frequency of that circuit. We can control the output of the LC oscillator by varying its capacitance, which will change its resonant frequency, that is 1 by under root LC. Then, with the help of the IF amplifier and the filters, all other noise is eliminated. Suppose you have to put up a channel at frequency equal to 93.5 MHz. So when you turn up the knob to 93.5 MHz marking, you are actually varying the capacitance of the LC oscillator circuit, that is, altering its resonant frequency. And as you alter the resonant frequency of the LC oscillator and the value of intermediate frequency being fixed, you get the output after filtering, which was modulated on a carrier wave broadcasted at 93.5 MHz. So this is the resonant frequency, and there exists a bandwidth of about 200 kHz. The existence of this bandwidth is the reason why a person can hear fainted noise of the channel even at 93.4 MHz and 93.6 MHz also.